Hi, welcome back to ARISTOTHINK. Today I'm going to show a physics video. It's been a long time since I don't post any physics video, but let's make it today. Now, I'm going to show exactly what's written here, step by step, but I want to show you from those equations that is going to happen. Look, this is a yo-yo, right? I don't know if you can see, but I'm pulling from the top. I'm also going to pull from the bottom, because I can choose, you see, from the top, you see, if I look from the top, the other is going to be, I'm going to pull from the bottom, but from the top first. Now, the center of mass is exactly at 0. Let's make like this so you can see better. 0, okay? Due to perspective, it doesn't seem so, but trust me, it is, because I'm looking exactly in front of it. Now, and this is going to be exactly at what, at 4? Let's see if it's okay. Now, look, 4, 0. Let's see. Look, as I move, can you see that the yo-yo is getting farther and farther away? I'm going to move up to 24. All right, 24. And the yo-yo is stopped exactly at 13.5. Okay? And if we do this math, the ratio, you see, one move with 10. Let's go. 10. Oops, yo-yo is back. 10 divided by 13.5. So this is 0.74. I'm expecting this to be at 2/3 because it's not perfect, okay? I'm not measuring the yo-yo, etc. But you see, so I'm going to prove to you that this is pretty close to 0.66. It's about 10% difference. I'm not worried about that. But now, so if I pull up from the top, the yo-yo gets behind. But look what happens if I pull from the bottom. Now I'm pulling from the bottom, you see? From the bottom. Now I'm going to make it like 10 to make it simple math. Okay? So can you see this knot? It is exactly at 10. Yo-yo at 0. I'm going to pull. Now look, as I pull, the yo-yo gets closer and closer. Closer and closer. And eventually, what? I move to what? 18, right? 18. The knot is at 18. And you cannot see. You see 18 and the center is 16. So you see, I pulled from 10 to 18, this knot, but the yo-yo moved it 16. I move it 8, my hands, but the yo-yo moved twice as much. I'm going to show you exactly in here why is that so. Now, camera in its place. Now, here, stay with me. Now, this is exercise. I have a cylinder. It doesn't have to be a yo-yo, right? Any cylinder. I'm going to pull that cylinder from the top, but then I'm going to pull from the bottom. There is a difference. Of course there is. Why? Because as I pull from the top, can you see that the yo-yo is like, I'm stretching this line. I'm taking more line of the yo-yo. Can you see? Because yo-yo is doing this, you see? So I'm taking more and more lines. So I'm expecting indeed the yo-yo to stay behind. So you see, the distance center of mass and A is going to increase. I'm expecting that because look, if I do this, can you see the system? You see, I'm taking the line away out of the yo-yo. But in here is the opposite because you see, in here, can you see from here? Yeah, let me just remove this part. You see, in here, as I pull from this direction, we both know now the yo-yo is going to come back to us. All right, let me put water in here so you can see better. Better. So you see, now, when I pull to the side, you saw the yo-yo, right? In both situations, the yo-yo comes to me, the same direction. But in here, it stays behind. And here, what's going on? As I pull, if the yo-yo is going this, now the line is being retracted into this system. So I expect the yo-yo to come closer and closer because this line is reducing. Agree? Now, we're going to see all that. And that's why I think it's important to show you the physics and also the yo-yo in here. Now, the question is, given this cylinder, now I want to find the speed of the center of mass relative to the ground. You see how the center of mass moves in respect to the ground and how the center of mass moves in respect to point A, my hands. Now, let's follow this. To start with, I'm going to ask you to look exactly in the middle of my blackboard. This should be enough. Now, the first thing we have, because I'm going to do only drawing, right? Not many equations. I don't like. It's not that I don't like equations, but if we can work with drawings, it's way better to understand what's going on than work with equations. My opinion, at least. Now, whenever you can draw, I draw. This is what I mean. So you see, look, this is an object. The red vectors are the translational part. So the translation going on to the right. Okay, I mean, just imagine a pure translation. You see, just moving. So every single point of that yo-yo cylinder is going to move together to the right. And this is the same vector VCM. All right, okay, they are all move equally to the right. But the yo-yo is also spinning, isn't it? So we have two motions here. The translational part, which is this, right? The yo-yo is just translating, but the yo-yo is also spinning, right? Rotating. So we have two. So the pure rotation, only this. This is pure rotation, right? Okay. Now, pure translation, this. Now, rotation and the translation. You see? So, due to the translation, we have the VCM. Due to rotation, we're going to have another speed, the tangential speed. And the tangential speed is going to be the V prime. I'm calling V prime. All right? Now, what's going to be V prime? It must be VCM. Because I didn't write, but I'm considering in most of cases, that is what's going to happen. I'm considering that there is no sleeping. So this the yo-yo is not doing this on the ground, you see. The yo-yo is stuck to the ground, moving without sleeping. So if there is no slippage in here, okay, on the ground, it means, let me take my chalk. If there is no slippage, it means that if I have a V because of the VCM, I gotta have another equally V opposite. Agree with me? Because look, this point must be zero, period. Must be zero. No discussion about it. If this is V, I don't have to tell you what's going to be the tangential speed. I don't. You have to find out. Because it gotta be the opposite of VCM. Because it's the only way that I'm going to have zero on this point. You see? Once I give you VCM, you already know the tangential speed. Must be the module of VCM. So this is going to be V prime in this direction, you see, every place is going to be V prime. But I have some special points. Now, if this is going to be upwards, right? The tangential speed, and also added into the center of mass speed. That means that this is going to be the net speed, right? Okay. Well, if you ride a bicycle, you know that when you ride a bicycle, what happens? When you ride a bicycle, you see our back is totally wet. Why? Because look, the water doesn't go only this direction. It goes a little bit more like this, you see? So if I had only the tangential speeds, probably the water would hit our heads, or not even our heads. Because it hits our back is because of this speed, okay? The horizontal speed with that one. Well, either way, what I wanted to recover from this image is this. On the center, I have only VCM. Now, in here, I have zero VCM. What about on top? At the top, something very weird happened. And what is going on? At the top, I have VCM, but I also have the tangential speed, as you can see here. And we just discussed it. They have the same module. That means that on top, at the top, the speed is twice. Yes. That means that the water droplets in here wets the front of whatever you're calling, you see, but it is faster than the speed of the object. It is. That is why at the top, the water goes in front. It beats us. Because, well, we have this translational, but we also have the energy of rotation, you see, speeding up. Now, I have 2 VCM in here, VCM and 0. And that's it. That is what I want you to remember from this drawing, because I'm going to use this drawing in here, all right? Now, this is just to recap. What I'm going to use is very simple now. Now, relative to the ground. I want to find the relative speed relative to the ground. So what's going to be? I'm going to use this triangle. Pay attention to this triangle, please. I just told you, this is going to be a triangle where 2 VCM, center is going to be VCM, this is going to be 0, okay? This is going to be this triangle translated into here. Well, what do I have? I'm pulling from this point. So I'm pulling, you see? I'm pulling A like this. It has V speeds. If I have speed V at A, well, it means that at this point, B, I also have the same speed, V. So this is going to be V, okay? This is the V I want to find. I want to find what's going to be V with connecting with VCM. So, triangle similarity. VCM is to V in the same way that R is to big R plus small r. Agree with me? Again, this is to that the same way that this like is to this like. All right? Assemble this and just move this up. VCM is V. Done. Now, from here, I want you to understand something. What's going to be bigger, V or VCM? Just look at the triangle. You can look at the algebra, but look at the problem itself. So V is clearly bigger than VCM. So it means that if I'm pulling here, V, this speed is clearly bigger than VCM. So only by that, we can say that the VCM is going to stay behind. All right, and that is what we can see from here. Let me just put it here. This. So what did I just say? That if we pull, let me put myself in here again. No, here. Can you see the blackboard? Okay, let's take the blackboard. It's better. Now, what I'm saying is this. Look in here at the image. If I pull from the top, you see, from the top, all right? I'm saying that V is bigger than VCM. So VCM is going to stay behind. VCM does not have the enough speed to cope with V, you see? And that's what I'm going to show you here. Now, in here. Let's go to the lab. You see? Look, in here. As I move from the top, this from the top, look, from the top, okay? As I move from the top, VCM does not have enough speed to stay close to this point. So it just moves away and away. You see, look, it's together, isn't it? It's going to increase resistance. Increase. Yeah. And that's what you can see from here. Okay. Back to its original place. So that's what you can see from here. All right. V is bigger than VCM. So yes, the yo-yo stays farther and farther away. Yes, of course, because I'm pulling in here. What's going on? The yo-yo is doing this. Can you see that the string is being unrolled? You see, I'm removing a string from the yo-yo. So the string is getting bigger and bigger. This because you see, in physics, if we don't understand what's going on, if we just get stuck to the formula, sorry, you become dumb. You see, the idea in physics is to try to see outside the equation, to see what's going on. And that is my job with everything that I teach. I like to teaching my students to perceive what is beyond the dumb formulas, I would say. Okay, now this is done, okay? Relative to the ground, beautiful. Now, relative to point A. Well, relative to point A, well, I want to know how is going to be the yo-yo, the cylinder, connected to my hand. So, what's going to be the speed of the yo-yo with my hands? Well, relative speeds, right? We saw that both are going in the same direction. Doesn't matter if it's B or at C, doesn't matter. The yo-yo is always going in the same direction, but what we need to see here is the relative speed is going to be the difference, agree? If they are both, well, if I have a 50 kilometers per hour and 30, what is the relative speed? 50 minus 30, agree? If they are both going in this direction, you see, the relative speed is going to be one minus the other. So we have to do a subtraction, but what minus what? That is the thing. So which one is faster? V, clearly. V is bigger than VCM, so the difference is going to be V minus VCM. You just read it here, you just pause the video. I'm not going to do this algebra, it's not the idea here. Besides, it's basic algebra, if it's not basic, ask questions later. I'll be flattered to ask, but now, let's just, the difference is going to be this, all right? Now, as we saw, VA is bigger than VCM. This is V, right? VA is bigger than VCM. So we're expecting the distance to increase. That's what we just saw. Now, the other way around is if we, here, let me show, is the other way around is if we, now, we take the yo-yo and move from the lower part, you see? From the top, and now from the lower part. I'm pulling from the low parts. And see? And as you see, the yo-yo doesn't matter how, you see? The yo-yo is going to get back. You see? Look. You see? The other way is different. I told you. The other way is different. It gets away from my hands, right? It stays behind because the speed of the yo-yo is not enough to stay with my hands. But in here, the yo-yo is going to be bigger. The speed of yo-yo is going to be bigger than my hands. And that's what I want to show you. Camera, please go the other side. Cameras. Okay, relative to the ground. Now, it's going to say, I'm going to the same triangle. You see? I didn't write because it doesn't matter, but this is going to be 2 VCM, right? But it doesn't matter. I'm not going to use this. I'm going to use this triangle. Here, see? Come on. I'm going to use this triangle and also this little one. So again, VCM is to V. VCM is to V. The same way that big R is to this difference, all right? So VCM is to V, big to small, okay? The same way that big R is to this, not to R, okay? We are comparing this big triangle with the tiny one, all right? So this distance is R minus R, okay? This, well, have this, send V to this part, so this is the center of mass relative to the ground, right? But now in this case, I know that VCM is bigger than V, okay? And if VCM is bigger than V, that means that when I do the difference, I'm going to do VCM minus V. Notice that in here, I did V minus VCM because V is bigger than VCM. You see, those things you have to be careful in physics, you see? It seems all the same, but it's not the same. It's totally different, you see? So V, and you do it opposite, your answer is going to be wrong. So V minus VCM, because V is bigger than VCM. But in here, I can see that VCM is bigger than V. So it's going to be VCM minus V. And that's going to be the speed of the center of, the relative speed of the center of mass relative to my hands is going to be this one. Well, and of course, because VCM is bigger than V, the VCM is going to be faster, is going to come closer and closer to my hand because the V of my hand is not enough. VCM is bigger, so I expect this distance to decrease, right? And makes sense, right? Because as I pull into this direction, what's going on? The yo-yo is pulling the rope, you see? It's pulling the rope, so the string is getting smaller. And now I'm going to show you, to finish this, I'm going to show something with this guy. Now, just to close, all right? I'm going to prove with numbers. Of course, this yo-yo is not exactly, but I'm going to assume it is close to, see? I'm going to assume it's close. Can you see? Try to, if you have real patience, you can try to get this radius, the big and small. You do the math, take a print. And I won't do this, man. I don't have the time. But if you want to do it, please do it and put on the comments later, okay? Measure, take a print, measure, okay? And try to find try to see if it, I'm going to do an experiment here and to try to see if it matches, all right? But I won't have the patience or time to do this. You can do it for me, please. Now, I'm going to thank you very much for that. Well, either way, now, so the idea is here. I'm going to assume that the yo-yo is exactly, small r is exactly half of big R. I'm going to assume that. So let's go to the lab. Let's go to the lab. Yeah, I'm very, the lab is very close to my office. Now, okay, well, we just saw, I'm going to move in here. Look, the camera, I mean, actually, look at the blackboard. We just saw that if I pull, look, if I pull from the top, can you see the blackboard, please? Okay, look, if I pull from the top, that's what's going on, isn't it? If I pull from the top, just like the drawing there, okay, what do I expect? Look in here, oops. All the way around. Look in here now. If I move from the top, now looking here, I expect what? VCM be smaller than V. So what's going to happen? VCM is not going to have enough speed to stay with my hands. So expect the yo-yo to stay behind, right? And let's see if this happens. Okay. Now I'm going to put like, you see, can you see this knot? I intend to put at 4, okay? At 4. This is 0. Because of the perspective, it seems not, trust me, the sensor is exactly at 0 because I'm seeing straight in this direction. I can see better than you have with the camera. Okay, I'm going to start at 4, start at 0, right? So center 0, this knot is going to be exactly 4. Okay, about 4. So not so much. It's difficult. It's not going to be. I believe if I have a result of about 10-15%, I'm more than happy. You see, you can say that it's getting farther and farther. Agree? Because it was pretty close. Now, did not start at 4. Agree? I'm going to go up to 24. This is 24. Enough. I move it. It doesn't seem so because of the perspective, but trust me, it is exactly over 24. You see, over 24. And the yo-yo, it is to what, 13.5. So the yo-yo moved from 0 to 13.5. And the knots move from 10. The knots move from 10. Wasn't it? No. From 4. From 4 to 24, wasn't it? Yeah. From 4 to 24. So the knots move 20. Let's put here. So the knot moved 20. Okay. But the yo-yo moved 13. So I'm going to do actually the opposite. So it's going to be 13.5, which is going to be the distance of the yo-yo, 13.5, divided by the big distance, which is going to be 20. Wow. That is crazy. Much better than expected. I was expecting 2/3. Gosh. I was expecting 2/3. But did you see how much you got? We get almost 2/3. Unbelievable. Unbelievable. So you see, look, what's going on is this. Can you see? Those are the results, right? Okay. That means that, you see, the yo-yo moved with 13.5. So the yo-yo, the cylinder, moved 13.5. But point A, this point going to be up, VCM, right? Center of mass. Okay. And point A moved with 20. Now, what's going to be this? If I compare, now I want you to pay attention to this. So we have seen, if we compare VCM with V, what is that supposed to be? I'm comparing the center of mass, and V is going to be my hands. All right? So we know that because of small r is going to be half the big R. So make this. Let's do this assumption here. So I'm saying that R is 2 small r. Okay? So 2 little r divided by what? 2 little r plus r. So it's going to be 2r over 3r, small r's, 2/3. Can you see this ratio? If I make r being 2 little r, that means that this ratio is going to be 2/3. And this is exactly 2/3. Exactly 2/3. And that means that if I divide 13.5 by 20, this is basically 2/3. We saw. You see, 0.66. I got 0.67. You see? 0.67. Wonderful. It works. It works. You see? Now I'm going to prove the other way around. Oh, of course. I'm assuming, and I can assume these no problems, that V is proportional to the distance, because we know that V equals delta S over delta T. Delta T is being constant, so V is proportional to delta S. So the ratio of 2/3 between speeds and center of mass, I can translate that into the distance. All right. Now, The other way around is going to be this. Now I'm going to show you what's going to happen here. Stay with me. Now I'm saying that this is going to be twice, right? This is going to be twice this small r. So only this part is going to be what? 2r divided by 2r minus r? Just r. 2. So now this ratio is going to be 2. Now, what does that mean? It means that VCM is twice as fast as V. So if VCM is twice as fast, I expect VCM to travel twice as much. Hold that. Hold that. I'm going to put exactly on the blackboard so you can see that ratio, right? So you see, look, exactly this. I expect VCM be twice as much V. So I expect VCM travel twice as much as my hand. V is the speed of my hands. Let's see here, from the bottom, right? From the bottom, you see? From the bottom. It's going to be about, all right? Okay, from the bottom, you see? I'm pulling from the bottom, okay? From the bottom. I'm going to start at 10, and this is going to be 0. A little bit more. I guess it's enough. Okay, 10, 0. Okay. Okay. Okay, now my hand moved 18. Didn't it? Yeah, about 18. And this moved about 16. Okay, can you see 16 here? So 18 for the knot. Okay. And 16. But remember that the knot was at 10. So the knot came from 10 to 18, moved 8. The knot moved 8. And the yo-yo moved 16. Yes, just as expected. Just as expected. You see? I proved to you that this reasonably is like little r is half the size of big R. And I showed how this actually works in here. So for me, that's amazing. That's why I think it's interesting to do physics, is because of that, to see this working in here in a very simple yo-yo without even measuring anything. We're just assuming like it's half. You can do the test, you see. Take a print and do it, you see. So you see, physics works, and the best of doing physics is to try to connect this with that, with a ruler, and reasoning. Does this make sense? Because if you gotta be willing to reason and see, yes, that is what I expected to happen. I don't want you to just see the formula and can't see what is behind. It is important. And that when you get to do this, you're going to love physics. And when you start loving physics, physics is going to be a very easy topic for you. But if you don't have that, it's going to be difficult to go one exercise after the other, because it's a hard road, I can tell you this. But if you love what you do, it makes things way easier. Thank you very much for your time. See you next time. Bye-bye.